In this presentation, I will present Task 2.2, Energy Ratings and Targets, and how to issue the ALDREN European Voluntary Certificate. The background is Article 11.9 of EPBD that says that the Commission shall, in consultation with the relevant sectors, adopt a voluntary common European Union certification scheme for the energy performance of non-residential buildings. The Renovation Wave initiative announced in the European Green Deal and the Commission Recovery Package aims to increase the renovation rate of existing buildings and their transformation into highly efficient buildings. Reliable tool and common metrics are needed for future actions and financial instruments to predict and prove the actual performance of building, to benchmark building performance with a comparable ambition level across Europe, and to avoid the lock-in effect by suboptimal renovation. The role of certificate is strengthened in the amendment of EPBD that asks for improvement of quality and transparency of certificates and of calculation methodology. I will talk about using the protocol for European voluntary certificates that aims to fill this gap and provide such tool and common metrics. European voluntary certificates provide harmonized benchmark and evidence of achieved energy performance and savings based on harmonized and transparent calculation methodology, creating a level playing field for products and services, harmonized and comparable indicators and benchmark on the scale, common template of certificate for reporting the results that can be issued before and after renovation. The standard energy assessment steps are required from assessors that consist of data collection, calculation of indicators, energy rating and benchmark on the scale, and finally issue European voluntary certificate. The important feature of European Voluntary Certificate is common calculation methodology that is based on CEN standards and ISO standards. That is a reference methodology in line with Annex 1 in EPBD, using obligatory the hourly calculation step. The software close to CEN standards based on hourly calculation step can be used. So any simulation software or in the future, perhaps European kernel on or accredited software for CEN standards. To be results closer to real consumption, that is aim of voluntary certificate is that climate of the specific location of building is used instead of the national standard climate or regional standard climate. National typical standard use patterns are used for calculation, for prediction for longer period, and for harmonization and transparency of calculation methodology, the Annex A is developed for overarching standards as asked by EPBD. The advantage of common calculation methodology is comparability, common European market for products, standards, software, and training and accreditation of experts. And one of Horizon 2020 projects, the CENCE project, aims to train assessors for voluntary certificate, European certificate. The ambition of ALDREN methodology is to be consistent, codified. This is why there is a link to existing European standards and European regulations. It wants to be realistic, so close to the real energy performance. This is why local climate is used for calculation. To be clear, simple, close to daily work of energy consultants and designers. To be international, so it means performed by international experts at the European level, able to work with CEN standards, and reliable, so ambiguous results, clear input and choices are set in protocol for for issue European voluntary certificate. In this table, you can see in which stage the energy performance certificate should be issued. So it is before renovation, then there is stage of design and construction works, and the certificate issued after renovation should confirm the achieved energy performance of building. Protocol for a European Voluntary Certificate provides step-by-step procedures from data collection to issue European Voluntary Certificate. It is reported in the table where is the description of each step, and also in the last column the source of information for expert where he can find the data. What is important is that in one column is indicated by green tick symbol. If the step is ALDREN methodology, it means something new proposed by ALDREN project. And in the empty cells, there are the general procedures reference to be applied by expert out of scope of ALDREN. So they are based either on expert daily practice or defined in other sources, for example, calculation according to CEN standards. Protocol for voluntary certification, voluntary European certificate has several chapters where describe each step of these procedures. I will focus in my next slides in most important steps which can influence significantly the results of energy performance assessment. So step 2 and 3, this is about climate and typical meteorological year for calculation. So firstly, location of building has to be defined in certificate by latitude, longitude, and altitude. Then the next step is that climate of specific location is used for energy calculation instead of national standard climate. So there is needed selection of nearest typical meteorological year for hourly energy calculation. And this should be based on Joint Research Center generator based on selection of locality that will show you my colleague after my presentation. The datasets are available in formats directly usable with the main building simulation software. After selection of typical meteorological year, the next steps is to allocate building to climate zone. There are 3 climate zones for which is set a scale. And this allocation is based on heating degree days, estimation from this typical meteorological year, and the rules to calculate these heating degree days are set by Eurostat. So you can see them here or directly in the website of Eurostat. So in this graph, you can see approximately the distribution of countries in these 3 climate zones, but these are heating degree days average for each country. So for specific location of your buildings, they can be different from country average. So this is just for illustration. Very important step that is a usual practice, so it is not something new in ALDREN methodology, is data collection that can be provided by building owner or collected by expert on site. All obtained data from building owner have to be verified and checked. Very important is to note that the number of input data depends on software used, and it may be less for hourly method than for monthly. Geometry is also based on usual practice, 3D modeling in simulation software, calculation of volume, surface area, form factor. But very important is how to set the reference floor area, which influence indicator. So step 9 describe in detail reference for floor area calculation that is used for building size normalization for indicator in kilowatt hours per square meter. And this reference floor area is defined as gross internal area calculated using the overall internal dimensions. As you can see in this picture, that means the floor area contained within the building measured to the internal face of the external walls, ignoring the internal partitions. Important is to say that the external walls define the heat exchange envelope of building you use for calculation, so that the reference floor area is coherent with your calculation of thermal losses. And this means that if some spaces are not included in your thermal envelope, if you do not calculate the thermal losses via the external walls, so such spaces are not included in calculation. Typical example are unheated basement with garage. So in step 7, the services included in calculation are described. So generally for offices and hotels, which are in scope of ALDREN project, only EPBD uses are included in calculation of energy performance. So it means heating, cooling and ventilation, hot water, lighting. It is important to note that for hotels, hosting functions are only included. It means the rooms, offices, bar, restaurants, sitting room, meeting rooms, they are included, but not non-hosting functions such as kitchen, swimming pool, a sauna are not included. In case they can be separated from building heat exchange envelope. Common indicators set in ALDREN and reported in other ALDREN certificate are harmonized with existing certification schemes. There was overview of needs by DGMB, HQE, and other simulation, other certification schemes. And these indicators are also compliant with levels, so that European voluntary certificate can be used as an energy module in these existing certification schemes instead of, for example, national certificate as they use sometimes today. So these indicators are some of them are important also for definition of nearly zero energy building, and they are marked in green in this slide. Step 13 is definition of standard use and indoor conditions. So for standard use, the national input data should be used. So they are related mostly to occupancy, the daily operating time, days of use, non-usage days, and very important at set point temperatures that differ per country. So there can be different requirements in each country, but you should be aware that there is European standard 16798-1 that specifies the occupancy schedule for standard use if they are not available at national level, but also specify indoor temperature limits that should be followed in your calculation. So it means, for example, that minimum temperature for heating should be 20 degrees. So if in some country there are national set point 19, so 20 degrees should be the minimum heating set point temperature. and similar for unoccupied period for setback temperature. Step 23 describe calculation of renewable energy ratio of total primary energy that is reported in European Voluntary Certificate. Calculation of this indicator should be according to European standard and ISO 5200-1. So it is a ratio of renewable primary energy to total primary energy, but what is important to note is that the perimeter choice for this indicator calculation should contain only renewable energy produced on site and nearby. Nearby is, for example, district heating, and renewable energy that is included in grid electricity considered as distant source is not included. More about calculation of this indicator, but also on other indicators, you can learn and be trained on it in CENCE project. Step 25-27 is important because it is about the produced renewable energy and calculation of self-use and export from this produced renewable energy. So calculation of auto-consumption or self-use and export is based on hourly step. So you can see in this graph below where is the in blue electricity use and in orange the PV production in buildings that not all produce electricity can be used in building. In some cases, so in this graph on the left side, you see potential difference due to calculation step. If you subtract the PV production in the yearly or monthly calculation step and comparison with hourly step. When you have calculated all the indicators, then there is a next step, that is the benchmark of the energy performance on the scale. The ALDREN scale is a relative scale based on ratio to the reference point. This reference point is expressed in kilowatt-hour per square meter, and it is approximately the cost optimal level from 2013 placed on the upper limit of energy class D. Class A is approximation to the nearly zero energy building definition in ALDREN. So the next steps, step 28, 29 is to choose the appropriate reference point on the scale for your building. So it is based on the climate zone estimated in the previous step and the building categories. So we have a reference point for offices and for hotels. And based on this climate zone, you choose, for example, for moderate climate, the reference value is 130 kilowatt-hour per square meter. This scale is based on simulation on several buildings for offices and hotels and for different climates, and now is still tested on the pilot buildings in the frame of ALDREN project. Next important indicator in energy performance certificate is thermal comfort score. that is reported together with energy and is based on the hours during occupancy when the operative temperature is outside the assumed intervals for indoor environment quality defined by European standard EN 16798-1. So you can see in this figure where is the variation of indoor operative temperature in two different buildings. One is existing old building and the second is nearly zero energy building. So both buildings are without cooling system, but you see that indoor environment in the nearly zero energy building is much better during the temperature extremes. So it was introduced by ALDREN, the thermal comfort score. In this example, you can see an improvement from original state after renovation of this indicator in one of pilot buildings. So what is important to say is that this thermal comfort score reflects the indoor environment assumed for energy calculation only. So it is based on typical meteorological year and standard operation of systems and not on the real comfort in the specific rooms. With the real comfort, deal with task 2.4 and the indicator called tail. Next step is issue or fill the common template of European Voluntary Certificate that consists of several pages. The first page, that can be also displayed in the building as the energy label, is the first page, and this page reports the energy performance classes, ratio to reference, energy performance indicators, main indicators which are related to energy classes. So it is a non-renewable primary energy balance with export allowed. So all produced renewable energy is counted. And the second indicator is related only to self-use of produced energy. So for example, PV only PV consume in building can be subtracted. So additional indicators in this page are energy needs for heating, cooling, lighting. That is a requirement also for nearly zero energy, ALDREN nearly zero energy building. Then it is final energy, total primary energy, CO2 emissions, renewable energy production divided to self-use and export, renewable energy ratio. It is reported also expenditure factor for overall final energy and thermal comfort score for winter, summer, spring, and overall thermal comfort score. I say that energy needs are also reported. So this decision is following recommendation by EPBD and by European Standard 5200-1 that energy needs are important and vital for a precondition for nearly zero energy building and to achieve a significant share of energy from renewable sources. So there is also set the threshold for nearly zero energy building for energy needs for heating, cooling, and lighting. Next page is overview of energy performance of building. So it provides really details about the energy needs per service, about deliver energy per service and per energy carrier. It is a calculation of primary energy on this page and the primary energy factors evident. It is reported produce renewable energy on site nearby and calculation of expenditure factors for each service and for overall final energy. It is also on this page you can find also more details about the thermal comfort score that is reported in the simplified way on the first page of certificate. Obligatory pages in energy performance certificates according to EPBD are recommendations for improvement of energy performance. So European Voluntary Certificate contains 3 pages with these recommendations, and but they are usually today very general. So there is one additional page which is optional with the detailed renovation roadmap that refers to task 2.6. So in these pages, you can find description of building and technical systems and recommendations for improvement. And in one page, there is also calculation of energy savings and potential achieve energy performance class after renovation. So it is important to say that in voluntary energy performance certificate is reported always a recommendation to the maximum and full renovation potential of building. The next and important optional page is about link between calculated and measured energy. The ambition of ALDREN calculation methodology is to be close to actual energy performance, and European Standard 15378-3 provides procedures for link of calculation with measured energy. And this link is based on energy signature and can be used for either calibration of calculation model that was used in our pilot building, in some pilot buildings, and can be used also for checking verification of real performance. So energy signature is visual connection between calculated energy performance and the measured energy. So it is dependency of power or energy consumption based on external temperature, and energy signature based on simulation is a reference to check by owner if the actual energy use is correct. What is needed to say is that this is not possible to use for all buildings because reliable measured data must be available from building. Here you can see example from 2 different buildings of comparison of energy signature that is developed from simulation. It is in green, and from the actual measured monthly energy consumption in gas. So you can see that in building on left side there was much higher consumption in comparison with the prediction, but in other buildings that was in reality really better operated. You can see very nice coherence between predicted and actual measured energy consumption. So based on simulation, that is results from calculation of energy performance of simulation, we can obtain the reference for check the actual energy use, and if there is some deviation, that can be investigated the reason and improve operation of building. For support the green investment, the high-performing buildings are highlighted by green certificate for ALDREN nearly zero energy building. So it is not sufficient to achieve energy class A to say that the building is ALDREN nearly zero energy building, but there is the hard race to get green certificate, and there are 4 requirements. It is energy class for the main environmental indicator of non-renewable primary energy balance. Then it is energy needs, heating, cooling, lighting, threshold that ensures good building envelope and geometry. Then it is thermal comfort score that has to be lower than set value. This should compensate the advantage of building with missing system, for example, without cooling, because this missing system is penalized by a lower thermal comfort score. And the last requirement is to be expenditure factor that is a ratio between building energy use and needs lower than 1.2. Higher ambition level is required for the financial support and subsidies, and this is the aim of ALDREN Energy Performance Certificate. So we did comparison of energy classes achieved by pilot office building on the ALDREN scale. You can see in this part of table for different stages of building renovation from original state to deep renovation, and we compare it with energy classes achieved in the on the national scale for mandatory energy performance certificates. So you see on this comparison not only much higher ambition level of ALDREN, that is the aim, but also the ability of ALDREN scale to show the intermediate improvements by shifting from one class on the other on the scale to the better energy class. Energy indicators are integrated in other tasks, so there is interconnection of the European Voluntary Certificate with other tasks. So I will show that just few examples. For example, in European Voluntary Certificate Plus, there are next optional pages, 1 page per each ALDREN task. So you can find here optional page for task 2.3, gap between measured and calculated energy, for task 2.4 on health and well-being, which evaluates really indoor comfort. And the page on task 2.5 about financial evaluation. This is an example of connection of energy ratings with the thermal environment and financial evaluation. So in this figure, you see connection of energy rating. It means primary energy from task 2.2 that is on axis X with the thermal comfort score that you see that by lower energy consumption it is better. So lower score is better score, and you see the financial valuation discounted cash flow based on the energy savings only. That is blue. These are the blue values, and also on energy and non-energy benefits if they are counted, such as higher renting rate or higher lower vacancy. So you see that increase of the financial value by improved energy performance and improved thermal comfort score in one of pilot buildings. So The aim of ALDREN EVC, European Voluntary Certificate, is to support communication between all involved stakeholders. So the aim is to provide some certificates that should be understandable by owner, have some visual interpretation of results. The aim is to provide tool for financial instruments and in such a way to support European policy to achieve European climate targets. So thank you for your attention.
Hello everyone, my name is Jean-Baptiste de Fouchier. I'm an engineer in research and development from the CSTB, and I've worked to apply the ALDREN methodology to pilot studies. And in this video, I'm going to illustrate the task 2.2 that is leading to the EVC that was presented by my colleague just before with a test case. As you can see in the upper, on the top bar, you will be able to track our progress that is leading to the EVC certificate. So the first step is to collect information, general information about our building. Here we took a typical building that is representative from office towers from the 70s with a surface of 30,000 square meters and 28 floors. It is located, yes, it is located in the region Île-de-France. Here you can see for the step 2 and 3, how to download the typical meteorological year. You go on this website and you select the location of your pilot, your building. Here our test case, and you can download the CSV file with all climate data here. Then we can move on to the step 4, where with the outdoors temperature, we can calculate the heating degree days and cooling degree days based on Eurostat methodology and equations. So here with the heating degree days, we take a base of 15 degrees Celsius and indoor temperature for winter of 18 degrees Celsius. And we obtain for our test case 2,628 heating degree days and 7 cooling degree days. When we got this value, we can move on to the step 5, where we can identify what is our climate zone. And we see that with our result in heating degree days, we are in the zone 2, the climate that is moderate. Here is a step that is quite independent from the others. It's to collect information concerning primary energy factors that are all in the table in this methodology of the task 2.2. Now we move on to a next step in the data collection concerning the building itself, all the thermal characteristics of our building. First, the utilities. We will include offices, reception hall that are at the ground floor and all the upper floors as well. And we'll exclude parking lots and technical rooms that are in the basement that are unheated. In the step 8, we collect all geometry information that usually are extracted from plans or 3D modeling when we already have them. And then step 9, we calculate the gross internal area. The gross internal area is the surface that we will use to calculate the energy, energy consumption. To calculate this gross internal area, we exclude the thickness of the external walls. We keep, however, the thickness of internal partitions. And to be coherent with the thermal losses calculation, we need to take only the parts that are inside the thermal envelope, meaning that all the parking lots and unheated space that are in the basement are not taken in account. Our reference is the International Property Measurement Standards, and you can refer to that for your own building. Based on a 3D modeling software, we calculated this GIA, and that gave us, for our test case, 25,800 meters squared. We now collect other information that are required for the BES simulation software. Concerning the windows, we have bands of windows with all double glazed that have a U value of 3. We have external walls made of concrete and with an extra insulation of 4 centimeters with a U value of 1.2. A flat roof at the top with concrete and a bigger insulation of 10 centimeters with a value that is under 0.3. We as well collect information concerning thermal bridges, etc. In the step 11, we collect information about air tightness. If we have already measured value, we take it. Otherwise, we use the default data from CEN standards. In the step 12, we collect information concerning the system for the heating. In our case, we have district heating with heat exchangers in the basement, the cooling with district cooling, the ventilation with an air treatment unit for all offices, and the lightings that, in our case, will use mixed technologies lamps. In the step 13, we move to another part of collection. We'll define the standard conditions. First, for occupancy and use, we can use either national standards. This is what we used for. We used the French standards for this test case, or we can use the European standards to define the occupancy and the temperature set points for the regulation. The same for system controls concerning the ventilation rate, the lighting's operating time, the HVAC controls, and we can use as well the European standards. And here in the step 15, we take the climate information from the step 3, and we can convert it into a file that is compatible with our BES software. In our case, with our software, we needed to convert it into a .ray file. Now that all the data collection process is done, we can move to the simulation and calculation phase. First, the simulation. For the simulation, we will first we need first to create the 3D modeling software, the 3D modeling of the building with our 3D modeling software, based on information that we previously collected on in the step 8 and 9. And this is how it can look like once this step is done. So you can here see the building with as well surrounding other buildings that we created a typical environment that could be in Paris. Once the 3D modeling is done, we can move on to the step 17 with the BES software, where we take information from the step 10 and 11 to complete all envelope information concerning the walls, the windows, the roof, and we precise as well the thermal zone. In our case, we have all floors from ground floor to the top, that is a thermal zone, and the basement that is considered as an unheated space for our simulation. Then in the step 18, we define the systems based on the information collected in the step 12. In the step 19, we'll define what are the modeling conditions based on those steps. So the system features, the operation settings, the controls. Then we can run the simulation with our BES software, and we collect the outcomes of this simulation. That is the annual final energy use per carrier in kilowatts hour per square meters annual. Once this is done, we can move on to the calculation phase, where the calculation, we will use the results of our simulation and the primary energy factors that we collect in step 6 to calculate the primary energy. We have first we calculate and we obtain 190 kilowatt hour per square meters a year, and we calculate as well the non-renewable one, 184. Then in the steps forwards, we calculate the renewable energy that is produced. Here in our test case, before renovation, we have no production. So the production is 0, the auto consumption is 0, and what is exported is 0 too. And therefore, those two other parameters that take this primary energy that is non-renewable and subtract the outer consumption, and that subtracts the electricity that's exported by photovoltaic panels, are all equal because we have no production here. Those two indicators here will be used for our scale in the energy rating. So now we can move on to the energy rating phase, where based on the steps 1, 2, and 4, we defined in the step 28 the reference point. So thanks to those steps in the data collection, we know that we are in a moderate climate zone. So we take the reference of 130 kilowatt hour per meter squared per year. Then we move to the step 29, where we can define our own scale based on this reference. We can calculate our own scale of different energy class. In the step 30, we calculate the results, the level of our building for our indicator here. We see that we are at 184, that is just a bit above 183, that is the boundary between E and F. So we are in the level, we are in the class F here for both indicators, for the both energy performance indicators. Now that we have the results for before renovation states with the label, the energy class F, we can wonder what to do, what to suggest for the renovation. And we have a method with within the ALDREN project that is called the renovation roadmap process. This renovation roadmap process will suggest different strategies of renovation based on different parameters such as the components characteristic that we want to renovate, the obsolescence, the owner's will, the energy gain, and the return on investment. And it will generate, as I said before, those two strategies for an immediate renovation and another one for full renovation that will be for a long-term plan. I want to say here that if you're interested in this process, if you want to learn more, you can look at the video on this task 2.6, the renovation roadmap process. There is a tutorial. Here to go on this tutorial about EVC and the task 2.2, we will take the full renovation results of the RenoMap. So taking this full renovation results, we have already the data collection process that is done thanks to the RenoMap. And we can now run the simulation. And once it is done, use the results to calculate the primary energy as we did before. And we see that this time we have a production of electricity and we export all this production of 2.6 kilowatts per hour per square meters a year. We export everything. So we have definitely now a difference between this indicator here that takes out the consumption and the exports. When we move on to energy rating, we can both indicators are in the class A. Here is our ALDREN scale, where we can see that our state before renovation of our test case is at the border between E and F with 184 kilowatt hour per square meter. Then the immediate renovation that is at the energy class D with 120 kilowatt hour per square meter. And the full renovation with 37 kilowatt hour per square meters with reaching the energy class A. Finally, we can produce EVCs. We can produce one EVC before renovation, where you can see that we have the energy class F, and another EVC for the full renovation with an energy class of A. You can see as well that the EVC is green, and this is because it reached the nearly zero energy building. And this is more than just reaching the label, the energy class A, but it needs as well to ensure that the thermal comfort is good in this part of the EVC, and it has like special requirements for energy needs as well that needs to be fulfilled.
There are several questions frequently asked by stakeholders, which we would like to answer now. So the first is, what is the link between the national and European voluntary certificate? So ALDREN European Voluntary Certificate is not to be considered as a competing instrument with the national mandatory EPC. They are complementary and both have an important role to play in the climate policy framework. So the difference is that the national mandatory EPC has to compare buildings against the national building stock, the cost optimality has to be taken into account, and the price of issuing the mandatory EPC is also an important issue, and it is not always easy to ask for hourly calculation step for mandatory EPC. The position of ALDREN European Voluntary Certificate is different. Higher ambition level is required for financial support, subsidies for non-residential buildings, and more accurate prediction of energy performance is needed in some cases for building owner for his proper decision-making process towards deep renovation, and especially for cost efficiency calculation that is needed for specific building location and really in more detail. The next question is, what is the link between the EVC and the RenoMap? So EVC is issued for current stage of building, so it means not only for building new constructed, and the recommendations for improvement are obligatory part of energy performance certificates and should be always given if there is some potential for improvement. Without the RenoMap, these recommendations are usually only very general, do not go in detail, do not calculate cost optimality, and do not provide individual steps in time. So RenoMap provides more details about timing, cost, also reported in separate optional page in a certificate. So there is a special page, and what is important, the full renovation potential for this RenoMap is reported and as recommendation for improvement in European voluntary certificate. So here is example for thermal envelope, but there are recommendations for systems and building control and other systems. More details you can see in a specific video on task 2.6 about the building renovation passport and renovation roadmap. The next question is why the thermal comfort is a requirement for ALDREN nearly zero energy building. It is also often asked if there is any difference between the thermal comfort in the European Voluntary Certificate and the one used in the method for tail in task 2.4. So the thermal comfort score reflects only the indoor environment assumed for energy calculation and not the real comfort in the specific rooms or specific building. So it is operative temperature obtained by calculation in hourly simulation software for energy performance estimation, for standard use of building and standard behavior of technical systems, and for the typical meteorological year. So for conditions for which the energy performance is calculated. Tail is related to actual measured indoor environment and actual building operation. Reporting this indicator, this calculated thermal comfort score, together with the energy performance, is important for comparison of solutions, as the better energy performance due to a missing system, for example, often missing cooling system, is penalized by worse thermal comfort score. So this is just to show improvement of indoor environment, even if perhaps the energy performance is higher due to install cooling system.
Question 4. How much time is required for the task 2.2? Approximately from 5 to 10 days for the calculation phase to calculate and to obtain all results to then fill out the different EVCs you want to produce. Here are the time-consuming steps that we identified. First, extracting the information from the documents. Indeed, we have usually a lot of information in those documents, and we need to sort which are relevant for us and which are not. The 3D modeling process can be as well type taking. It really depends on the building shape. We have as well the thermal bridges calculation that can be harder or easier depending on the tool assistance you have in your BES software. And you have as well the system settings that, according to your BES software, it offers you more or less details, and that will change the time you will need to fill this information. As well, another important point is that it really depends on the assessor's experience. If he knows well the software he's using, if he knows the tips, and as well, if he knows the modeling process and the key points and what are the priorities, what is useful to do, what is not, he can save a lot of time if he knows that. I hope this video was helpful for you, and I thank you. Goodbye.